Okay. So, hi Jason. That's right. So we're going to be talking today about the trig antiderivatives. And actually there's going to be a fair derivatives. There's going to be a fair amount of work that you guys are going to be doing. So at various points in the video, I'm going to stop the video and have you guys work at home, those of you who are listening at home. And the first thing that I want you to do, actually, is to create a list of the 6 trig derivatives that we have, the derivatives of the 6 trig functions, starting with the derivative of sine x and ending up all the way over here with the derivative of cosecant x. So go ahead and do those 6 at this time. Okay, and so you should have these 6. The derivative of sine x is cosine x. The derivative of tangent x is secant squared x. The derivative of secant x is secant x tangent x. And over here, the derivative of cosine x is negative sine x. The derivative of cotangent x is negative cosecant squared x. And the derivative of cosecant x is negative cosecant x cotangent x. Just like so. Now, we have these 6 derivative rules. Our next step in the process then is to turn them into antiderivative rules. So that each one of these now gives us an antiderivative. For example, the antiderivative of sine x is negative cosine x plus c. Notice how I handle the negative sign here. Because the scenario is most common to have the antiderivative of sine x by itself, then I wrapped up the constant negative 1 into the antiderivative right there, so that when I take a derivative, I get a double negative to give me sine x back. Everybody see that? So following this idea, go ahead and write the 6 trig antiderivatives that come from these rules. Go. All right, let's see if you have them. How does this become an antiderivative rule, Mark?
The antiderivative of cosine is not just sine.
It's just sine, right? There's no mystery about whether there's a negative sign in there. Yeah, exactly. Tony.
Antiderivative of secant x is equal to tangent x plus.
Jennifer. Pick one. Yes. Plus C. Good. Clara.
Antiderivative of secant x cos tangent x 3x equals secant x.
Good. And then the last one, the antiderivative of cosecant squared x dx is negative cotangent x plus c. And you'll notice that for all 3 of these, I wrapped up the negative sign into the result here because this is the common scenario that we're confronted with, and so it makes sense to have a rule that we can use. Okay. Does this make sense to everyone? Now, there's a couple of different directions that we can go here. Before I go too far, I want to point out that we have a gap that we don't know what to do with yet. Notice that our gap is that we do have the antiderivatives of two basic trig functions, but we do not have antiderivatives for the other four. We don't yet know how to antidifferentiate tan x, or secant x, or cotan x, or cosecant x. We'll fix that later, but much later. But we don't have those yet. Instead, we have the 6 antiderivative rules that come from the derivatives of the 6 trig functions. So currently we have 6 antiderivative rules whose results are the 6 trig functions. Okay? That's the first thing. And the second thing is that armed with these 6 and trigonometric identities, we can make a lot of headway. So in the theme of algebra first, meaning that if you are looking at an antiderivative and you're not sure what to try algebra first. We can roll into that the algebra of the trigonometric identities. In particular, I want to remind you of the 3 Pythagorean identities. Sine squared x plus cosine squared x is equal to 1. Everybody knows that one. But then they're liable to forget 2 very useful ones. If I divide through by cosine squared, then I get tan squared x plus 1 is equal to secant squared. Or if I take the original and divide through by sine squared, I get cotangent squared plus 1 equals cosecant squared. Now, why do I say that these are useful to us when integrating? Well, consider this antiderivative. I look at it and go, that's not one of my 6. So then I think, all right, let me try some algebra first. Do I have any identities that have tan squared x as a particle? I could write that as sine squared x over cosine squared x. But I look at this and I go, did that help me? Well, not really, because I end up with a quotient and it's kind of getting. So that's a worthy consideration, but I'm going to put that in my back pocket. Anything else?
Secant squared minus 1.
Aha! There we go. If I employ the Pythagorean identity to rewrite this as secant squared x minus 1, look at that. I now have an antiderivative that I can actually evaluate. Tan x minus x plus the mandatory constant c. So by use of the trigonometric identities, I turned an antiderivative that I didn't know what to do with. You might represent this with a confused question mark sign into an antiderivative that I knew what to do with. And it's the magic of trig IDs that made it happen. But wait, there's more. Consider this one. The antiderivative of cosine x over sine squared x. I look at this guy and I think, again, not really sure where to go with this. Perhaps I could rewrite this in terms of other trigonometric functions. So if I were to take and split factors like this, all of a sudden I realize, oh, I'm looking at the antiderivative of cotangent x times cosecant x, which is negative cosecant x plus c. And so what we ended up with was a manageable antiderivative by using trigonometric identities and some algebra in order to rewrite. Now, obviously, this was a clever move. It required some cleverness. So how do you acquire that cleverness? One thing will definitely help you, and that is that if you commit to really knowing your trigonometric identities well, then when you see them, your brain will go, ooh, I know what to do. Try this one. Go. Mark, do you have an insight?
You can use a pattern identity to substitute 1 minus the sine squared x for sine squared x.
And so our integrated becomes what?
Square root of sine squared x,
Which is,
sine.
at least when sine x is positive. Yep. And that is what?
That is negative cosine.
Exactly right. Good. Here's an advanced one, if you really know your identities. What do you think? If you don't remember, go ahead and look up the identity for sine 2x.
I remember that function.
Remember it? Okay.
Yeah.
Anybody got it?
I think that last scenario
What is another way to write sine 2x?
is 2 times sine times cosine.
Yes, it is. 2 sine x times cosine x. And now Jennifer carry it home for us.
So it's 2 cosine.
Which is?
2 sine.
And there you go. Good. That's exactly it. Well, at this point, we've had the lesson, so to speak. What I'd like to do at this point is just do some practice with antiderivatives. So, let's just practice. find the antiderivative? Go.
So do we need to get breakdown from last week?
For the previous problem? No. Oh, I see what you're saying. In other words, you're concerned about a couple of places where sin x does not exist. Sorry, where sin x is 0. The real reason that we don't worry too much about that is that all of those places where sin x is equal to 0 are ultimately going to give us, removable discontinuities. And so we figure we could catch those holes if we needed to. That's the spirit, especially when you do complex calculus with complex numbers. The spirit of removable discontinuities is let's just go ahead and catch them and not worry about them.
Okay.
That's a good question. Okay, what do you have? Clara.
7 over 4 x 4 2x squared plus x.
Did you check it? Good. Very good. Okay, let's try this one. Go. Tony, you got one for us?
Negative.
Give us the process.
Oh, okay. So I convert this equation into 3x minus x squared plus 1 and times x to the negative 2.
I like that. Yep.
And 3x to the negative 1 minus 1 plus x to the negative 2. So the equation is negative 6 x to the negative 2 and minus x plus x to the negative 3 over negative 3 plus 3.
How did you get? Did you check this?
It's negative 6x to the negative 2.
Negative 6x. Okay. Did you check your answer?
I don't have time for that.
Okay. Why don't you check it right now? Tell us what you find here. 'Cause I'm a little uncertain about a couple of things going on. There and there. What did you find when you took the derivative of that first term?
I actually divide instead of
Yeah, but not only that, when you add 1 to this power, you don't get -2. And when you add 1 to this power, you don't get -3. So we actually need to come back and rethink our lives a little bit. This is not the correct antiderivative. Let's start here. The -x was correct. And what about the x to the -2 power over here?
x to the, it's negative x to the negative y.
There you go. Now, finally, let's go back over here and consider 3x to the -1 power. The antiderivative of 3x to the -1 power. If you try power rule, you end up dividing by 0. That's our warning sign that we've forgotten about a special exception to our power rule. Yes, what is the integral of x to the -1 power? Yes, except we need one more thing. We need to take care of our domain. It's the natural log of the absolute value of x. Sometimes it's easier to see it if you write 3x to the -1 power as 3 over x. So you want to match these two mentally in your mind to that antiderivative right there so that it makes sense to you. Okay, now of course we need to check it. So go through term at a time and check for me. What's the derivative of the first term?
3 over x minus y plus
That's 1 over x squared. And now combine with a common denominator to get 3x minus x plus 1 all over x squared. Do we have a match? We do. Wait, did I miss anything?
There was an x squared.
Oh, here, sorry. Yep. It was so firmly fixed in my mind, I thought it was there. Okay, now, just for comparison's sake, find the antiderivative here. Duh. You got this, Jennifer?
Yeah.
Go ahead.
So it's 2x to the
Give us the process first.
another x to 1 to minus x to the negative 1.
Good. Everybody see how she went ahead and rewrote this as times x to the minus 1/2 and distributed. And it's appropriate to be able to do algebra at that level. Good. Keep going.
So it's 2x to 3 over 2 over 3 minus 2x to 1 over 2 plus.
That's it. Okay, check it. Okay.
Then we shall also.
If I rewrite this, I get the square root of x minus 1 over the square root of x. And that equals x minus 1 over root x. Notice that when I get the common denominator for that first term, root x times root x is equal to x. Okay. Now, one of the things about this problem that's kind of interesting is that I could also have rewritten the integrand of this. And when I write it like this, sometimes students will make a silly mistake. And the silly mistake is one that I want to alert you to so that you don't do it. The silly mistake is what I call every fraction is a log mistake. Okay? So sometimes what students do is they know that the antiderivative of 1 over x is natural log of the absolute value of x. And so therefore they conclude that the antiderivative of 1 over anything is a natural log form. It's not. This is not a log form because it is not specifically in the form of 1 over x or x to the minus 1 power. In fact, it is in the form of x to the minus 1/2 power. And that's a perfectly good exponent for use with the power rule. Every exponent works except for minus 1. So the moral of that story is be aware of the special exception. The antiderivative of x to the minus 1 is a natural log. Everything else, all other powers of x, we can use the power rule. Does that make sense? Okay. Well, at this point, we have a couple minutes left, but at this point, you guys have done well enough. I think we're going to call it a day. See you tomorrow.